Hello everyone, welcome to this video on electronic configuration in which we are going to learn about distribution of electrons in various atomic orbitals within the subshells of a shell. So after this discussion, the complete location of electron within the atom can be identified. Okay, so let's get started with it. In our previous video, we have learned and understood writing electronic configuration of various elements. We had taken the example of sodium and iron whose electronic configurations are displayed right over your screen. So if you are familiar with writing electronic configuration of elements, then you can move ahead in this video and see their distribution in various orbitals. However, if you are finding it a new information to yourself, then please watch the previous video in this series and then you can resume the video from here. For the time being, we are moving ahead and going to study the distribution of electrons in various orbitals of the mentioned subshells. Okay, let us take the example of sodium to understand the electronic configuration in orbital level. The electrons are filled in the orbitals in accordance with the Pauli's exclusion principle, which says the pairing of electrons start only after each available orbitals have received at least one electron. Okay, so let us learn its explanation through the example right here. In 1s subshell, we have only one orbital, which is represented by this square box right here. Similarly, in 2s subshell also we have just one orbital. In 2p subshell, which has 6 electrons in it, we have 3 orbitals. Okay, right here. And again for 3s we have just one orbital. So when we start filling these orbitals with electrons, we must fill it in such a manner that each of the available orbital in that respective subshell has got at least one electron before start pairing. So filling the 1s subshell with 2 electrons, it will follow as first electron and then second electron. Similarly for 2s subshell, first electron and second electron. Now coming to 2p6 configuration, we will start filling the electrons by giving one electron to each of the available orbitals. That is, one electron goes here, then second electron goes into the second orbital, followed by third electron into third orbital. Okay, and only after each of the available orbital have received one electron, the pairing will start. So fourth electron will pair with the first electron, then fifth electron will pair with the second, and sixth with the third. Okay, so this is how we will fill the electrons in respective orbitals of a subshell. Now only one electron is available in 3s, so the filling will follow like this. Let us apply the same principle in case of iron. We will represent all the available orbitals in the form of square boxes. Again, 2p orbital has 2p subshell has 3 orbitals and 3d subshell has 5 orbitals right here. Okay, so we will start filling as 1s2, 2s2, 2p6 coming to 2p6. We will fill one electron in each orbital, then start pairing. 3s2, again 3p6 will follow the same procedure. Now coming to 3d6, we have 1, 2, 3, 4, 5 electrons, and then pairing will start. Okay, and finally 4s2. Okay, now let us try to write the electronic configuration of Fe2 plus. So the 4s2 electron is the outermost electron in the ground state of iron. So when iron forms Fe2 plus, it will lose 2 electrons from this subshell, the outermost subshell. Okay, so the configuration will become 4s0. It has lost the available 2 electrons in its outermost shell. Similarly, iron also forms Fe3 plus cation by losing an additional electron from 3d subshell as well. Following the same order, we can easily write the electronic configuration of the elements up to atomic number 30. The last 10 elements of this group will belong to D block elements, and this will create the third period of the periodic table. The order will be as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d subshell will be filled one by one from 1 to 10. Following this order, we can write the electronic configuration of chromium as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d4. Similarly, for copper atom whose atomic number is 29, we will write the electronic configuration as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d9, because there will be 9 electrons left finally. Okay, so these are the electronic configuration that we will write using the rules that we have learned so far. However, there is yet one more rule which we need to follow in order to correctly arrive at the electronic configuration of atoms such as chromium and copper. So let us have a look at that. We just wrote the electronic configuration of chromium atom in various subshells. In various orbitals, the same distribution can be represented as shown. Our interest right here is in the outermost configuration of chromium atom, that is 3d subshell and 4s subshell. Now, talking about 4s subshell, it can hold a maximum of 2 electrons, and it has got its 2 electrons. Such arrangement will be called as fully filled arrangement. So 4s subshell of chromium atom is completely filled. Okay. Talking about 3d subshell, we know that it has got 5 orbitals, and out of 5 orbitals, 4 of them are occupied by the electrons. Okay, so 4 of the 5 available orbitals in 3d subshell are singly occupied, we can say like that. All right, now there is a possibility that if one of the electron from 4s subshell jumps into 3d subshell, the vacant orbital of 3d subshell, then each of the available orbitals in 3d subshell will have one electron as well, isn't it? And such configuration in which each of the available orbitals are singly occupied are called as half-filled orbitals, and such electronic configuration, either half-filled orbitals or fully filled orbitals, are relatively more stable, and therefore the chromium atom tends to follow this configuration, in which there are 5 electrons present in the 3D subshell and only 1 electron present in the S subshell. So the correct electronic configuration of chromium is 1s2, 2s2, 2p6, 3s2, 3p6 and 3d5 and 4s2 instead of 3d4, 4s2. This is because such arrangement will give all the atomic orbitals in d subshells 1 electron each. Okay. Same discussion will follow for the copper atom as well. However, in this case, the shifting of electron from 4s subshell to 3d subshell will result in a fully filled electronic configuration in the d subshell of copper atom, and therefore the electronic configuration of copper is 3d10 4s1 instead of 3d9 4s2. Okay, so please keep this electronic configuration in mind. These are very important exceptions up to the atomic number 30. In this video, we learnt about the distribution of electrons in atomic orbitals. With this, we have concluded our discussion on electronic configurations over a series of 4 videos. I'd like to request you to watch all of them so that you can have a firm understanding over this topic. I'd also like to request you to share this video among your friends and subscribe to the channel for more such topics. Thank you so much for watching and see you in the next video.